Okay, so today our goal will be to discuss a piece of theory which establishes a nice relation between compact and Fredholm operators, but which was created long before the general notion of a Fredholm operator was introduced. This theory was developed mostly by Rees in 1918. And also some important results were obtained by Schauder in 1930. So now the union of their results is usually called the Rees-Schauder theory. This theory is very important because it has numerous applications, and not only in functional analysis, but also in some neighboring fields of mathematics. Also, this theory provides a rich supply of Fredholm operators of index 0. And it was one of the main motivations for Dieudonné to introduce general Fredholm operators in the 1940s. Well, the main message of the Rees-Schauder theory, this theory deals essentially with operators of the form 1 plus k, where 1 is the identity operator on a Banach space, and k is a compact operator. And the main message of this theory is that each operator of this form is a Fredholm operator of index 0. So this is essentially the main message of the Rees-Schauder theory, which, by the way, when we combine this principle with some standard tricks from the duality theory, this result easily implies, for example, the classical Fredholm theorems on integral equations. Okay, so let's start with some algebraic preparation. Suppose that X is a vector space and T is a linear operator on X. We introduce some notation. We denote by Kn the kernel of T to the power n, and we denote by Rn the image of T to the power n for each non-negative integer n. So we obtain two chains of vector subspaces. The first chain is increasing, and the second chain is decreasing. It can happen that one of them stabilizes, and there is a special terminology for that. So we give the following definition. We define the ascent of T as follows. This is the minimum number n, such that Kn equals Kn plus I for each non-negative integer I. And if there is no such n, if this chain doesn't stabilize, then we say that the ascent of T is infinite. If T equals infinity, if there is no such n. In Russian, ascent is подъем. And duly we define the descent of t to be the minimum number n, such that the second chain, the chain of the images of the powers of t, stabilizes starting from n. And again, if there is no such n, then we say that the descent of t is infinite. And in Russian, descent is спуск. Okay, let's now prove some properties of these numbers. We have the following lemma. Lemma 1. First of all, I claim that if kn equals kn plus 1 for some n, then actually the chain stabilizes starting from n. That is, kn equals kn plus I for each non-negative integer I. And so in this case, t has finite ascent. Similarly, if we assume that Rn equals Rn plus 1 for some n, then the chain of the images stabilizes starting from n. I have this equality for each non-negative integer I. And so in this case, t has finite descent. And finally, part 3. Part 3. If t has finite ascent and finite descent, then the ascent and the descent are equal to each other. Okay, so now let's try to prove this result. Essentially, this is purely linear algebra. In particular, 1 and 2 are very simple exercises for you. Well, maybe let 1 be an exercise, and let's see together that 2 is also very easy. Well, indeed. To prove true, it suffices to show that Rn plus 1 equals Rn plus 2. Because if this is the case, then we apply it again, and we see that Rn plus 2 equals Rn plus 3, and so on. Okay, so let x sits in a Rn plus 1. And we want to show that it sits in Rn plus 2. So we can write x in the following form. X is t to the power n plus 1 of y for some element y in our space. We write it in the following way: t applied to Tn of y. So Tn of y sits in Rn, but by assumption, Rn equals Rn plus 1. So we can write the element t to the power n of y as t to the power n plus 1 of z for some element z in our space. So as a result, we see that this is t to the power n plus 2 of z, and this sits in n plus 2. And that's it. So we see that n plus 1 equals n plus 2. Okay, now part 3. We want to show that if t has finite ascent and finite descent, then the ascent and the descent are equal to each other. Well, let's show that I'll prove only one half of this result. I'll prove that the descent is less than or equal to the ascent. Well, to prove this result, let's assume that this is not the case. So suppose that the descent is strictly bigger than the ascent, and let n denote d of t minus 1. Well, in this case, since n is strictly smaller than the descent, we see that n is strictly bigger than n plus 1. But n plus 1 is already the descent, and so n plus 1 equals n plus 2. And on the other hand, since we assume that the descent is strictly bigger than the ascent, this implies that kn plus kn equals kn plus 1. Okay, so let's try to obtain a contradiction. So let x be an element in Rn. So we can write x in the form Tn of y for some element y in our space. Okay, now we apply t once again, and we see that t of x equals Tn plus 1 of y, and Tn plus 1 of y. And this element sits in n plus 1, but by assumption n plus 1 equals n plus 2. So we can write this element as Tn plus 2 of z for some element z in our space. Okay, this implies the following. If we compare these two expressions, we see that the element y minus, oh, sorry, this is a typo here. I said n plus 2, Tn plus 2 of z. So here we use the assumption that this element sits in n plus 2. So it can be written in this form. Okay, now if we look here and we take y minus t of z, we see that this element sits in kn plus 1, in the kernel of t to the power n plus 1, which is equivalent to this equality. Okay, but we let's now recall that kn plus 1 equals kn. So this element sits in kn. That is, if we apply t to the power n, we get 0. Or equivalently, this means that t to the power n of y equals t to the power n plus 1 of z. And t to the power n of y is our initial element x. And so we see that x sits in n plus 1. Okay, so we see that an arbitrary element x from Rn actually sits in Rn plus 1. And so this implies that Rn equals Rn plus 1. And this is a contradiction because we assumed from the very beginning that Rn is strictly bigger than Rn plus 1. So this contradiction shows that d of t is indeed less than or equal to a of t. And a similar argument shows that the opposite inequality is also true, and this is an exercise for you. Okay, so module of this exercise, this is the end of the proof of lemma 1. So this is our lemma 1. And we also need one more pure algebraic lemma, lemma 2, which gives us a so-called risk decomposition. Risk decomposition. So again, we assume that X is a vector space. X is a vector space. And T is a linear operator on X. And we suppose that T has finite ascent and finite descent. Suppose that the ascent of T is finite and that the descent of T is finite. So we already know that in this case, they are equal to each other. So let P denote the ascent, and we know that P, the same number, is equal to the descent of T. So let Kp denote the kernel of T to the power P, and let Ip denote the image of T to the power P. I claim that in this case, X decomposes as direct sum of Kp plus Ip. Moreover, each of these subspaces is T invariant. Kp and Ip are T invariant. T restricted to Kp is nilpotent. And T restricted to Ip is an isomorphism of Ip onto itself. Is an isomorphism of Ip onto itself. So essentially, this result states that if you have an operator of finite ascent and finite descent, then this operator decomposes as direct sum of two pieces, of two blocks. The first block is nilpotent, and the second block is bijective. Okay, so let's try to prove this. First of all, we show that X is the sum of Kp plus Ip. So let X be an arbitrary vector in our space. And let's apply T to the power P to this vector. Of course, this vector is in IP, just by the definition of IP. But since P is the descent of T, P equals I to P. And so we can write this element as T to the power 2P of Z for some element Z in our space. And now let's introduce a new element X prime, which is T to the power P of Z. So let's draw a picture which explains this construction. So if this is our initial element X, we apply T to the power P. This is T to the power P of X. So we observe that it comes from some element Z after we apply T to the power 2P. And then we apply T to the power P to Z, and we get a new element X prime. So this is a picture which explains our construction. Okay, now what happens if we apply T to the power P to X prime? Well, this is T to the power P of Z, that is T to the power P of 1. This shows that or what is y? We have no y. Sorry, this is a we have no y. This is T to the power P of X. T to the power P of X sits in IP, and here we have T to the power P of X, which is equal to T to the power 2P of Z for some Z. So we have this equality. And this means that the X minus X prime sits in KP. And so we can write now our element X in the following way. This is X prime plus X minus X prime. So X minus X prime is just a moment. So this element X minus X prime sits in KP, and X prime by construction, look here, by construction X prime sits in IP. And this formula implies that X is indeed the sum of KP plus IP. Okay, so let's now show that this sum is the direct sum, that is the intersection of KP and IP is 0. So let now X be an element in the intersection of KP and IP. So, well, X sits in KP, and this means that T to the power P of X is 0. And since X is in IP, this means that X can be written as T to the power P of Y for some element Y in our space. Okay, so if we combine these equalities, we see that T to the power 2P of Y is 0, which means that Y sits in K2P. But P equals the ascent of T, so K2P equals KP. And this means that Tp of y is 0. But Tp of y is nothing but our initial element x, which was in the intersection of Kp and Ip. And so this argument shows that the intersection is 0. The intersection is 0. And so x is indeed the direct sum of Kp and Ip. Good. So now to complete the proof, we have to show that T restricted to Kp is, well, first of all, it's clear that both of them are invariant, that this is immediate from their construction. So clearly, Kp and Ip are T invariant. And it's also clear that T restricted to Kp is nilpotent, just by the very definition of Kp. So now to complete the proof, we have to show that T restricted to Ip is bijective, is an isomorphism. Okay, first of all, if we apply T to Ip, what we get is Ip plus 1, again by the very definition of these spaces. But Ip plus 1 equals Ip, because P is the descent of T. And this means that the restriction of T to Ip is a surjective map of Ip onto itself. Well, on the other hand, we already know that the intersection of Kp and Ip is 0. So the kernel of T, which is K1, it is obviously contained in Kp. So the intersection of the kernel of T with Ip is 0. And this means exactly that T restricted to Ip is injective. So it is an isomorphism of Ip onto itself. And this completes the proof of lemma 2. Okay, so this is the end of our algebraic preparation. We can now prove the fundamental theorem of the Riesz-Schauder theory, which is due to Riesz. So now we are in the framework of functional analysis again. Suppose that X is a Banach space. T is a bound linear operator on X, such that T is of the following form: is the identity map plus a compact operator. So I write this in this form. So it sits in the set of compact operators shifted by 1. Then we have the following results. First of all, I claim that T is a Fredholm operator and the index of T is 0. The index of T is 0. Second, I claim that T has finite ascent and finite descent. And finally, part 3. This is a kind of analytic form of the risk decomposition. So let P denote the ascent of T, which is the same as the descent of T. Let Kp denote the kernel of T to the power P, and let Ip denote the image of T to the power P. Then both Kp and Ip are closed T-invariant subspaces. So here the new word is closed. I mean, U compared with lemma 2. So they are closed T-invariant subspaces. Moreover, Kp is finite dimensional. Also, X is the direct sum of Kp and Ip. T restricted to Kp is nilpotent. And finally, T restricted to Ip is a topological isomorphism of Ip onto itself. Okay, so this is our theorem. So again, essentially part 3 states that our operator, which is of the form 1 plus a compact operator, is decomposed into two blocks, two pieces, two blocks. The first block is a nilpotent operator acting on a finite dimensional space. And the second block is a topological isomorphism of the second subspace onto itself. Okay, so let's now prove this result. So we write T in the following form. This is 1 minus S. It will be more convenient for me to write minus instead of plus, where S is a compact operator. Now the proof will be divided into several lemmas. Or several steps, maybe. Several steps. Step 1. Let's show that the kernel of T is finite dimensional. And the image of T is closed. By the way, well, let's recall that we already know that the image of any Fredholm operator is closed. But in this case, it will be more convenient first to prove that the image is closed, and then to deduce from this that that operator is Fredholm. Okay, so the proof of step 1 is quite easy. First of all, so let K denote the kernel. Let K denote the kernel of T. So T vanishes on K, and this means that S restricted to K is the identity map of K onto itself. But since S is compact, so the restriction of S to K is also compact. But we know that the identity operator on the bound of space is compact if and only if the space is finite dimensional. So the kernel of T is finite dimensional. Okay, now we have to show that the image of T is closed. So let's consider the quotient of X modulo K. And we consider the induced operator T hat from X modulo K to X, which acts by the following formula. So this is the operator induced by T. And it is injective because we quotient out the kernel of T. And to show that the image of T is closed, it suffices to show that T hat is topologically injective. Well, indeed, the image of T and the image of T equals the image of T hat. And if T hat is topologically injective, then of course its image is closed. Topologically injective means that there is a positive constant C such that T is bounded below, T hat is bounded below by C, in the sense that for each element U in the quotient, we have the following inequality. So in other words, if we write this in terms of T, this means that T applied to X is greater than or equal to C times the norm of X plus K for each X in our space. Okay, let's suppose that this is not the case. Assume that there is no such C. And let's try to get a contradiction. Well, there is no such C. This implies that there exists a sequence Xn in X such that the norm of the respective coset in the quotient is 1. For each n, but T applied to Xn goes to 0. Well, this is more or less immediate from this inequality. So if there is no C which satisfies such an inequality, then we take a C equal to 1 over n. We normalize respective vector Xn in a suitable way, such that the norm of the normalized vector is 1, and we get this. So the norm of T of Xn in this case will be less than 1 over n, so it goes to 0. Okay, let's now recall the geometric meaning of the quotient norm. So this norm is nothing but the distance between X and K. And this is 1 for all n. Okay, now let's observe that we can also assume from the very beginning that Xn is bounded. We may assume that the sequence Xn is bounded because the norm of xn plus k is 1. And so by the definition of the quotient norm, we can always find a representative of this coset such that the norm of this representative is, for example, less than or equal to 2. So we can always assume from the very beginning that xn is bounded. Otherwise, we just choose different representatives in the same cosets. Okay, so xn is bounded, and S is a compact operator. So the image of the sequence sits in a relatively compact subset. And so we can choose a convergent subsequence from S of xn. Without loss of generality, we may assume from the very beginning that the sequence S of xn converges. We may assume that S of xn converges to some element x in our space, because S is compact. So because if this is not the case, then we just choose a suitable subsequence of xn. Okay, so S of xn, what is this? So this is xn minus txn, because well, S is 1 minus t. But t of xn goes to 0. T of xn goes to 0. And so this means that xn also goes to x. Xn goes to x. So we apply t. We see that t of xn goes to t of x. But t of xn goes to 0. So this implies that t of x is 0. That is, x is in the kernel of t. X is in k. And this is a contradiction, because let's recall that the distance between xn and k is 1. And xn converges to x. And this is impossible. This is a contradiction because xn goes to x, and the distance between xn and k is 1. Okay, so this is the end of the proof of part of step 1. So we have shown that the kernel of t is finite dimensional and the image of t is closed. Okay, now step 2. Step 2. I claim that t is Fredholm. T is Fredholm. The proof is a nice application of the duality argument. Well, indeed, we already know that the image of t is closed. The image of t is closed. So the core kernel of t is a Banach space. So we want to show that this core kernel is finite dimensional, because we already know that the kernel is finite dimensional. And we want to show that the core kernel is finite dimensional. But, well, let's now look at the dual operator. T star is, well, t is 1 minus s. So T star is 1 minus S star. So it is operator. It is an operator of the same form, 1 plus a compact operator on the dual space. But we have already proved that the kernel of each such operator is finite dimensional. And now we apply the closed image theorem, which was proved at the previous lecture. So we know that for each operator with closed image, the dual of the co-kernel of T is isomorphic to the kernel of T star. This isomorphism holds for each operator with closed image. But the kernel of T star is finite dimensional. So the dual of the co-kernel of T is finite dimensional. And this implies that the co-kernel of T is itself finite dimensional. And since the kernel of T is finite dimensional by step 1, we conclude that T is Fredholm. Okay, so we know that T is Fredholm. The next step is to show that T has finite ascent. This is step 3. The ascent of T is finite. Well, again, assume that this is not the case. Assume that the ascent of T is infinite. And this means that all the kernels of the powers of T are all different from each other. So Kn is strictly smaller than Kn plus 1 for each n. We now use the Riesz lemma on an epsilon perpendicular. So for each natural number n, let xn be 1/2 perpendicular to Kn in Kn plus 1. One-half perpendicular to Kn, which means that the norm of this element is 1, and that the distance between xn and Kn is greater than or equal to 1/2. So we get a sequence of vectors in our space. We'll try to get a contradiction with the compactness of the operator S. So basically, we will show that the sequence Fs of xn doesn't have a convergent subsequence. This will be a contradiction because S is compact. So we take any two natural numbers n and m. Let's suppose that n is greater than or equal to n plus 1. And observe that we have the following inequalities. First of all, we apply our operator S to xn and then to xm. So what is this? S is 1 minus t. So this is, well, let's write it 1 minus t xn minus 1 minus t xm. So explicitly, this is xn minus txn minus xm plus txm. Okay, now let's observe that t of xn sits in kn, because xn sits in kn plus 1. And xm, well, xm sits in kn plus 1, and kn plus 1 is contained in kn, well, because of this inequality. So we see that when we calculate the norm of this vector, so what can I say about the norm? So all this expression, I mean, all these three vectors are in kn, and xn is 1/2 perpendicular to kn. So by the choice of k of xn, we conclude that this is greater than or equal to 1/2. And this is a contradiction with the compactness of the operator S, because clearly such a sequence S of xn doesn't have a convergent subsequence. And so the image of the unit sphere, of the unit ball, is not relatively compact. Oh, this is a contradiction with the compactness of S. So the contradiction shows that the ascent of T is finite. And this is the end of the proof of step 3. Okay, now we have to show that the descent of T is finite. And this is step 4. Here, to prove this result, it will be convenient to use the duality argument. Well, indeed, we already know that if we take the dual operator T star, it is also the form 1 plus a compact operator, so it has finite ascent. We already know that the ascent of T star is finite. So there is a natural number n, such that the kernel of T star to the power n equals the kernel of T star to the power n plus 1. Okay, let's now take the pre-annihilators of these kernels. First of all, T star to the power n is nothing but T to the power n star. So take the pre-annihilators of these kernels. And let's now recall that the pre-annihilator of the kernel of T star is the closure of the image of T. It holds for each bounded operator between norm spaces. So this is the closure of the image of T to the power n. And this is the closure of the image of T to the power n plus 1. Well, but we already know that T is a Fredholm operator. So T to the power n is also a Fredholm operator. And the image of a Fredholm operator is closed. So we see that the image of T to the power n equals the image of T to the power n plus 1, which means that T has finite descent by lemma 1. Okay, so the descent of T is finite. Now to complete the proof, we have to prove there is decomposition for T. So let's recall the statement. We also have to show that the index of T is 0. So we have to prove part 3, and we have to prove that the index of T is 0. Part 3 is almost immediate from lemma 2, from the algebraic Riesz decomposition, which holds for each operator with finite ascent and finite descent. So the only point which is new in part 3 of this theorem is that first of all, these subspaces are closed. Well, but Kp is closed because it is the kernel of a bounded operator, and Ip is closed because T to the power p is Fredholm. And the Fredholm operator has closed image. And this is step 5. So we now know that T to the power p is Fredholm. So Ip is closed. And Kp is finite dimensional. And finally, lemma 2 implies that we have the direct sum decomposition, and that T restricted to Ip is not just an algebraic isomorphism, but is also a topological isomorphism by Banach's inverse mapping theorem. So lemma 2 implies 3. Because T restricted to Ip is not just an algebraic isomorphism, but is also a topological isomorphism. By Banach's inverse mapping theorem. Okay, so this completes the proof of part 3. And finally, to complete the proof of our theorem, we have to show that the index of T is 0. But here we use the Riesz decomposition. So what is the index of T? So T is the direct sum of two blocks, T restricted to Kp and T restricted to Ip. And it's immediate from the definition of the index, that in this case, the index of the operator equals the sum of the indices of these two summands, namely the index of T restricted to Kp and the index of T restricted to Ip. But the first summand is 0. The first index is 0 simply because Kp is finite dimensional. So we have already observed some time ago that each operator on the finite dimensional vector space has index 0. And the second summand is also 0 because T restricted to Ip is an isomorphism of Ip onto itself. So its index is 0. So as a result, we see that the index of T is 0. And this completes the proof of theorem. Okay, let's now look at some corollaries. Corollary 1 is the so-called abstract Fredholm alternative. the abstract Fredholm alternative. So if I have an operator T of the form 1 plus a compact operator on the Banach space X, then such an operator is injective, even only if it is surjective, even only if it is bijective. Well, indeed, this is an immediate corollary of the Riesz theorem, because we know that this operator is a Fredholm operator of index 0. And since the index is 0, we see that the kernel is trivial, even only if the co-kernel is trivial. That is, the injectivity is equivalent to the surjectivity. Corollary 2 is due to Schauder. It was proved in 1930. And this corollary is essentially an abstract form of Fredholm's theorems. So again, suppose that T, I should write the inclusion here. So T is an operator of the form, the identity operator plus a compact operator on a Banach space. Then, first of all, I claim that the kernel of T and the kernel of T star are both finite dimensional, and they have the same dimension. Second, the image of T equals the pre-annihilator of the kernel of T star. And finally, part 3, the image of T star equals the annihilator of the kernel of T. Well, from our point of view, this is indeed a trivial corollary of the Riesz theorem, because, well, we know that T is Fredholm of index 0, and we have proved at the previous lecture that the index of any Fredholm operator is the kernel of T, the dimension of the kernel of T minus the dimension of the kernel of T star. So part 1 of corollary 2 means precisely that T is Fredholm of index 0. And parts 2 and 3, again, from our point of view, they are trivial, because we know from our previous lecture that parts 2 and 3 hold for each operator with closed image. This is a part of the closed image theorem. And the Fredholm operator has closed image. So from our point of view, indeed, this is a trivial corollary from Riesz theorem. But this wasn't the case in 1918 when Riesz theorem was proved, and this wasn't trivial in 1930. So this result wasn't trivial, and it was originally proved by Schauder. By the way, if we apply this result to the special case where the respective compact operator is the Hilbert-Schmidt operator, a Hilbert-Schmidt integral operator on the big L2 space, then this result becomes, so these 3 statements become the classical Fredholm theorems on integral equations. Well, the details you will see the details in exercises in exercise sheet 2. Okay. Finally, let's now apply the Riesz theorem to the study of the spectrum of a compact operator. the spectrum of a compact operator. So just in case, let's recall the definition of the spectrum. Suppose that X is a Banach space over the complex numbers, and let T be a bounded linear operator on X. Then the spectrum of T is the set sigma of T, which consists of those complex numbers lambda, such that the operator T minus lambda 1, where 1 is the identity operator, is not invertible. Or equivalently is not bijective. And let's also recall that the spectrum contains the so-called point spectrum. The point spectrum of T is set denoted by sigma p of T, and it consists of those elements of those points lambda on the complex plane, such that the kernel of T minus lambda is non-trivial. And the elements of the point spectrum are called eigenvalues of our operator. So clearly the point spectrum is contained in the spectrum, and it follows from the elementary linear algebra that in the finite dimensional case, the spectrum and the point spectrum are the same. But on the other hand, there are many natural examples which show that if X is infinite dimensional, then generally the point spectrum can be strictly smaller than the spectrum. The most canonical example is the operator of multiplication by the coordinate on the interval. So if you take space, for example, big L2 space on the interval 0, 1, and consider the operator, which takes each function f of t to the function t f of t, so it multiplies by the coordinate, then the spectrum is the same interval 0, 1, but the point spectrum is empty. And this is more or less typical for operators on infinite dimensional spaces. So our next goal is to show that if our operator is compact, then the spectrum and the point spectrum are almost the same. So the only point which is in the spectrum, but which is not necessarily in the point spectrum, is 0. So we have the following theorem. So suppose that T is a compact operator. X is a Banach space, and T is a compact operator on X. Then we have the following results. First of all, if lambda is a non-zero point in the spectrum, then lambda is actually an eigenvalue. It sits in the point spectrum. Also, lambda has finite multiplicity. Lambda has finite multiplicity, which means that the respective eigenspace is finite dimensional. The respective eigenspace is finite dimensional. And finally, lambda is an isolated point of the spectrum. lambda is an isolated point of the spectrum. Okay, so this is part 1. And part 2, the spectrum of T is at most countable. So briefly, this theorem states that the spectrum of a compact operator consists of at most countably many isolated points, non-zero isolated points, which are actual eigenvalues of finite multiplicity, and 0, which is not necessarily an eigenvalue, which is not necessarily isolated, but it's the only point in the spectrum which is not an eigenvalue. Okay, so to prove this result, we observe that since lambda is non-zero, we can write the operator t minus lambda 1 in the following form. And so this operator is essentially of the form which was described in the Riesz theorem, because it is, well, it is 1 plus a compact operator and multiplied by a non-zero number, which is not essential here. So this implies that the Riesz theorem, or more exactly the Riesz-Schauber theory, applies to our operator. Because it is essentially 1 plus a compact operator up to non-zero factor minus lambda. Okay. Let's now observe that this implies that lambda is an eigenvalue. Well, indeed, this operator is not invertible because lambda is in the spectrum. So the Fredholm alternative implies that this operator is not injective. That is, lambda is indeed in the point spectrum. Also, we know that our operator is Fredholm. T minus lambda is Fredholm. In particular, this implies that the kernel is finite dimensional. That is, lambda has finite multiplicity. Okay, now let's show that lambda is an isolated point of the spectrum. To prove this, we will use the Riesz decomposition. So, as in the proof of the Riesz theorem, we let P denote the ascent of t minus lambda 1, which is the same as the descent of t minus lambda 1. We let Kp denote the kernel of t minus lambda 1 to the power p, and Ip is the image of the same operator. So we know that Kp and Ip are closed, and well, formally they are invariant with respect to t minus lambda 1, but of course this means exactly that they are t invariant. follows the T invariant. And X is the direct sum of Kp and IP. Well, what can we now say about the spectrum? It's clear that if you have such a direct sum decomposition, then the spectrum of T is the union of two pieces. This is the spectrum of T restricted to Kp and the spectrum of T restricted to IP. In other words, well, this is equivalent to say that an operator, such an operator is invertible if and only if the restriction of such an operator to both the subspaces is invertible. So it is not invertible if and only if at least one of them is not invertible. Okay. Okay, let's also observe that Kp is non-zero. Kp is non-zero because, well, already the kernel is non-trivial. And so the kernel of the same operator to the power p is non-trivial. Non-trivial. Let's look at the spectrum of T restricted to Kp. So we know that since we applied this theorem to T minus lambda, we see that T minus lambda restricted to Kp is nilpotent. T minus lambda restricted to Kp is nilpotent. And the spectrum of a nilpotent operator on a non-zero space is zero. So the spectrum of this operator, T minus lambda restricted to Kp, is zero. So the spectrum of T restricted to Kp is lambda. Okay, let's now look at the spectrum of the restriction of T to IP. So we know that T minus lambda restricted to IP is a topological isomorphism of IP onto itself. Which means that zero is not in the spectrum of this operator. Zero is not in the spectrum of this operator, T minus lambda restricted to IP. Equivalently, this means that lambda is not in the spectrum of T restricted to IP. Now, if we denote this equality, say star, then this equality becomes the following. It takes the following form. The spectrum of T equals lambda. And now we have the disjoint union of lambda and the spectrum of T restricted to IP. The union is disjoint because lambda is not in the spectrum of T restricted to IP. But the spectrum of each operator is a compact set. And in particular, the spectrum of T restricted to IP is compact. And so it is closed in sigma of T. And now the above formula. This formula implies that lambda is an isolated point. its complement is closed. So it is an open subset in sigma of t that is an isolated point. And this completes the proof of the first part of our theorem. So we have shown that each non-zero element of the spectrum is an eigenvalue of finite multiplicity and is an isolated point of the spectrum. And now to show that the spectrum is at most countable, well, essentially this is immediate from part one. Well, indeed, for each natural number n, let Kn denote the intersection of the spectrum with the complement of a suitable neighborhood of zero. The intersection of the spectrum with the set of those lambda such that absolute value of lambda is greater than or equal to 1 over n. So Kn is a compact set because this is a closed subset of the spectrum. Kn is compact. And by part one, all points of Kn are isolated. Obviously, this implies that Kn is finite. Kn is finite. And if we take the union of all these Kn's, so the union of all of them is obviously the spectrum minus 0. So we conclude that it is at most countable. And this completes the proof. So the spectrum of each compact operator is at most countable. All non-zero points in the spectrum are eigenvalues of finite multiplicity. And the only point of the spectrum which is not necessarily an eigenvalue is 0. And by the way, since if we assume that our space is infinite dimensional, then of course 0 is always in the spectrum, because a compact operator is not invertible. Okay, so that's all for today. At the next lecture, we specialize to operators acting on a Hilbert space. And our main result will be the classical Hilbert-Schmidt theorem, which tells us everything about the structure of compact self-adjoint operators. So we will see that each compact self-adjoint operator on a Hilbert space is diagonalizable in a suitable sense. We will obtain some more information about compact and also not necessarily compact self-adjoint operators on a Hilbert space. Okay, thank you.